Welcome everyone. I'm Andro, and together with my partner Stipe, we will give an overview of our reproducibility work, namely re-improving interpretability faithfulness for vision transformers. So let's start. Recently, vision transformers have achieved impressive results in computer vision. To better understand their decisions, researchers often use post-hoc interpretability methods, highlighting the most relevant pixels in an image using attention maps or gradient-based techniques. The problem, however, is that vision transformers are quite vulnerable to adversarial attacks, such as PGD, and this vulnerability extends to the interpretability methods as well. In other words, even small changes to the input can cause the explanations to shift drastically. So, how do we address this problem? Who proposed a solution called Faithful Vision Transformer? The key idea is simple. Make sure explanations stay consistent even when the input is slightly perturbed. How does it work though? They take a standard vision transformer and apply a method called Denoised Diffusion Smoothing, or DDS. And what exactly is DDS? It's a two-step process. First add Gaussian noise to the input image, then use a guided diffusion model to remove that noise. The cleaned up samples are then passed into the vision transformer, which makes the model both more robust and more faithful in the explanations. This way, explanations remain stable under adversarial attacks, improving both trustworthiness and performance. Therefore, our goal of the paper is, first, we validate the experiments and results reported by WHO. Then we extend their work by improving the method and examining both its plug-in flexibility and its environmental impact.
Now on to our methods. The original paper investigated two tasks and we reproduced both. The first task is image segmentation under a PGD attack. More specifically, the image is corrupted by using PGD and is inputted to the FViT. Then, an interpretability method is used to extract the per pixel relevances of the image. From this, a soft segmentation of the image is computed and compared to the ground truth. The second task is image classification under perturbation. Here, we first extract the pixel relevances by using an interpretability method and then mask out a percentage of the most or least important pixels. The perturbed image is fed to the FViT and a classification is computed. This is done for each portion of the pixels, and finally, an AOC value for all the portions is computed. Now onto our extensions. The authors investigated DDS in combination with transformer attribution. We proposed and investigated DDS with Attribution Rollout, a newer and supposedly better method. We did this for both segmentation and classification tasks. Then, we investigated DDS's plug-in nature with baseline interpretability methods in the segmentation task. Then, and finally, we investigated the runtime of using DDS and estimated the subsequent environmental impact. For the segmentation task, we used the ImageNet segmentation subset. We opted not to use the other two datasets which were used by the original authors due to missing scripts and model weights. For the classification tasks, we used the 2012 ImageNet validation set. However, we only used a subset of it because of very expensive runtimes on the full dataset. Similarly, for the segmentation tasks, we used only 2 out of the 3 models, specifically the FViT and the FViT. This was again done because of missing model weights and scripts. For the classification tasks, only the original FViT was used and we replicated this fully. Guided diffusion was used for our backbone of DDS, and this was also done in the original paper. Furthermore, we investigated all 5 baseline interpretability methods. These consist of raw attention, VATCAM, rollout, LRP, and transformer attribution. In combination with this, and as mentioned, we also investigated the recently introduced attribution rollout. Now we'll go on to the results, first starting with original tasks and the segmentation under PGD attack. Although the exact values that we reproduce are not exact, the general trends still prevail, namely TA as well as TA with DDS have the highest metrics across the board. A similar story can be said for classification under perturbation. This can be applied for both positive and negative perturbation, where either the most or least relevant pixels are masked out first. Here we can also see a hint of our first extension, namely attribution rollout combined with DDS improves over all other methods. Now onto our extensions, which are mostly consisting of the segmentation task. We can see in the first table that unfortunately, DDS doesn't improve metrics for most baseline interpretability methods. But for AR, it results in a massive increase and also results in the best overall method. Possibly the largest result of our experiment can be seen in figure 3, namely using DDS over a baseline interpretability method results in a much higher environmental impact. Finally, as a small bonus, we decided to reproduce the visualizations made by the original authors. As you can see, they match quite similarly.
Our findings are the following. DDS shows a slight edge over the approaches. While the exact numbers vary, the overall performance patterns remain consistent across methods. Swapping TA with AR inside DDS leads to better results. One drawback is that DDS comes with a substantial increase in CO2 emissions, and finally, when DDS is added to baseline models, it doesn't really change their performance in a meaningful way. Unfortunately, there were some limitations as well. Only certain subsets of the datasets were considered, meaning the findings might not fully generalize. Out of the 3 transformer models available, the study focused on just 2, and some assumptions had to be made because the authors didn't provide complete code or detailed experiment settings. Finally, for future work, one path forward is exploring lighter denoisers, for example through distilled UNets, distillation, or fine-tuning. Another idea is to cut down the number of steps by using adaptive noise scheduling, reducing it from hundreds to just few, maybe 3 to 5. Ultimately, the goal is to move toward an efficient real-time version of DDS that balances robustness with interpretability. We hope you have enjoyed our video.